Hello, year 13s, and welcome to this lesson on probability and significance. So today we're just going to be recapping um, what is meant by probability and how we use significance to determine if our data is significant or not, and what the sort of scale for measurement is around that. So we're going to start off with a bit of context. So our learning objective is just to go over what is significance and a significance level, and we're going to be looking at type 1 and type 2 errors and how they link to significance. So the running theme for today's lesson will be based around this particular task or this particular study where women are better at map reading than men. So here we can see as a directional hypothesis, we've got the IV first, DV, and then IV. So women are better at map reading than men. Results: on average, women answered one more question correctly than men on a map reading test. And the conclusion for this was, again, women are better at map reading than men, and that proves our hypothesis. So going over what we've spoken about in lesson, we always need to find a way to prove or disprove our hypothesis. And unfortunately, it's not as straightforward as that. We can only infer that the same is true for the population. And by doing this, you would have to carry out some sort of inferential test. And that inferential test will determine whether or not there is a significant difference between the males and females. As I mentioned before, if we determine that the data or the findings have occurred by chance, then it would be incorrect to conclude that that women are better than men at reading maps. And if we are adamant or sure that it could not have arisen by chance, then our data or our pattern is seen as significant. And that's where we have the 0.05 element there to sort of guide our chance or probability. Okay, therefore, the lower the probability of chance, the more significant the results are. So what we'd like you to do as your task, pause the video and write a null hypothesis and an alternative hypothesis for the study in the beginning activity. Okay. Okay. So when it comes to a null, we know that that means there is going to be no difference. So we always have that as a fallback hypothesis, so that when it comes to the findings and whether or not our data is significant, we have a direction to go towards with regards to whether we accept or reject our alternative hypothesis. Okay, so if our data is not significant, then we reject our alternative and accept the null. And if it is significant, then we accept our alternative and reject the null. You have to have that balance there, so you know what you reject and what you accept based on the actual findings. Okay, so like I said before, if it is significant, we reject our null. If it's not significant, then we accept our null. So you can't always be 100% certain, like we said, and we use the probability of 5%. Okay, so that means that there is less than or equal to a 5% possibility that the results occurred by chance, meaning we are 95% sure that there is that connection, that we're identifying that gender does play a role, or that women are in fact better than men. We're 95% sure of that. Okay. Now we always use 0.05. If we use 0.01, that means our probability is more stringent, and that scale for significance and that scale for difference between the two groups has to be higher. And if it's more lenient, then the probability is going to be 0.1. And that means that, again, the scale for that difference existing doesn't have to be as high as it usually is. And there's pros and cons for both of these sort of probabilities. However, in psychology, we always use 0.05. You will never use 0.01 or 0.1, but you have to understand why we use 0.05 and why we don't use the alternatives. So when to use stringent p-values? So drug trials, one-off studies, large difference, critical and calculated values. Now here, what it's saying is that we use stringent p-values when we have to be adamant or we have to be incredibly sure that our data was or is purely down to what we're measuring, and that there is only a 1% chance that, again, it could not be what we're ascribing the reason to be. Okay, so again, this is another diagram for you to understand that. So have a go at writing these as a percentage, and then rank the probabilities in terms of how likely they are that results were due to chance. Okay. This is the least significant probability range because it's the closest to 1. In other words, it is there is a higher likelihood that the results were down to chance rather than the actual IV that we're sort of measuring. Okay. So it's going to be the opposite direction. So the further away it is from 1, the more stringent it is going to be, and the less likelihood the results are due to chance. Because again, we're 99% sure, or 98, 97, 96, 95, whichever probability scale you're using. The further away it is from 1, the greater we are sure that it is not down to chance, because that gap for chance is so small that it makes our data, again, incredibly significant. But it's also quite hard to always guarantee that, because if the scale for, or the requirements needed to be deemed significant is so high, that if it always, even though a trend and a pattern is definitely clear and it exists, we can't always be sure that it's going to meet that. That's why 0.05 is that sort of sweet spot. Okay, and we've done this before. So again, we know it's 0.05. Degrees of freedom, or what you might find is that there is the number of participants based on the study used. You'd go along with that, and you'd find the actual correct hypothesis, or sorry, you'd find the correct critical value based on also the hypothesis used. Okay, just to recap, we've done this before. So, just a quick check. Identify the letters used to signify significance difference, or the significance level. Explain the reason for using inferential testing. Explain what is meant by the phrase significant. Suggest one reason why a researcher might use or choose to use 0.01 in preference to 0.05. Okay, so pause the video and answer these questions. Now, once you answer these questions, submit them to me. I'll show my homework as well, please. What we are also going to do now is we're going to be looking at type 1 and type 2 errors. So false positive and false negatives. Okay, so I've mentioned this before in class to some of you, and just try and explain, or in your own words, or write down what these images are suggesting, and also which error do you think is more dangerous and why. Okay, so we've got a false positive, you're pregnant. We know that a man cannot be pregnant. However, that pregnancy test for some reason has determined him pregnant. And we have a female here who was clearly pregnant, but for some reason the pregnancy test is determining that she is not pregnant. So these are some issues which you might encounter, and we would address these through the use of appropriate probability scales. So with a type 1 error, we reject a null hypothesis when we should not, and this creates a false positive. Okay, so we reject a null hypothesis. So we reject the idea that there is an influence or there is something there when we know that we shouldn't, because we know it's quite clear. However, this will create a false positive. A type 2 error is where we accept a null hypothesis when we shouldn't. and this creates a false negative. So again, we know that the hypothesis isn't correct. We know that we should be accepting the type or the alternative hypothesis. However, because the spectrum, or because there's a greater risk of chance in this particular scenario, it creates a false negative because the requirement needed. Now, a type 1 error refers to a situation in which we assume that our findings show something when they don't. Okay, so it's an optimistic error. In this instance, rejecting on a null hypothesis that is true and having to wrongly accept the alternative and assuming the results were due to the IV when they were in fact due to chance. Okay, that's going to be where, again, there's too much freedom. Okay, there is a risk of type 1 errors occurring if we set the p-value too leniently, so at 0.10 or 10%. So because there is a higher probability value, it increases the possibility that the results were due to chance. So because it's not strict enough, there's more room for error and more room for false positives. So that's why, again, 0.10 is deemed too lenient, because there's too much room for error and it can create false positives. On the other hand, a type 2 error refers to a situation in which we may miss something that is actually happening. So accepting a null hypothesis that is false, wrongly rejecting the alternative hypothesis, and assuming the results were due to chance when they were in fact due to the IV. And this is when things are too stringent. Okay, so 0.01% or 1%, that's saying that we have to be 99% sure that the data or the findings were due to the IV that we're manipulating or what we're measuring. However, because it is so high, because the requirements needed is so high, that we can sometimes get false negatives because it's just too stringent. The requirement can't be met. We know already, and it's pretty clear, but because it is too stringent, we don't always get that significance level. Okay, but we have to have this level because if we're testing new drugs or new medical treatments, we have to be adamant and we have to be as sure as we can. But this is where the issues do come in. Where do you find the balance? And the balance is 0.05. Again, recap: rejecting a null when we should not, p level too lenient, type 1, accepting a null when we know we should not, p level too stringent. Memorize this for me, please. Now, and this is why it said setting a p-value is kind of like a balancing act. Again, you've got to try and find the right balance between avoiding both a type 1 and a type 2, and the 0.05 is again the sweet spot. So, pause the video, have a go at answering these two questions, and then submit them for me. And in a moment, we'll talk about the answers. So pause the video, and then you can green pen your answers. So the first question reads: a researcher sets a level of significance at p less than or equal to 0.01. Explain how this may result in a type 2. And your extension, explain how a type 1 and a type 2 error affects the interpretation of the research of findings. Or of the findings of research, apologies. So first answer, compare this to your own. As a p-value is stringent, this means that there is a little room for chance occurring in our results. A type 2 error is when you accept the null hypothesis incorrectly. This means that there is little room for chance by having a stringent p-value. And this may have missed a significant difference. Second question: a researcher must be very careful when setting a p-value, as using a value that is too lenient might result in a type 1 error, and a researcher might think that they have found something significant when they haven't. On the other hand, setting a p-value that is too stringent might result in a type 2 error, where a researcher is too strict and might accept the null when in fact they have found something significant. However, in some cases where research cannot be repeated, setting a p-value of 0.01 might be appropriate. Okay, so compare your answers, green pen, or add any points in which you might have missed out on. But that's the importance of understanding what a type 1 and a type 2 error is.